play.
So now we have something really obligatory. You have to obligatorily listen to Professor Chueshov's lecture on synchronization in coupled stochastic PDEs. And please welcome.
Okay, thank you very much. It is a great pleasure for me to participate in this program and this beautiful place. I am here for the first time, and I like this place is very much, and also Cambridge is, of course, fascinating. So I will speak about synchronization and coupled stochastic PDEs. My talk based on especially based on some joint results with these people, Thomas Karabalya from Sevilla, Peter Kloiden from Frankfurt, and Björn Schmalfus from Paderborn. This is some plan of my lecture. This is main items which I will discuss, but then appears some more detailed explanation what will follow later. I first give some general rough idea of what means synchronization. Then my talk is really consists two parts: some example of synchronization of parabolic SPDE, and some application of theory invariant and inertial manifolds to problem of synchronization. Synchronization, there are a lot of people involved in this synchronization stuff, and I think first was Christian Huygens. Him in that time he studied problem of synchronization from scientific point of view. Of course, people observe synchronization forever. But from mathematical point of view, he studied synchronization of two pendulums, and it was important. It was how to say problem goes from military forces. They need to synchronize the chronometers in sea battleships in order to use it in war deals. On synchronization, a lot of publications. I list here only some monographs, and papers is 1,000 about it. But all these results mainly deals with finite dimensional systems. And for infinite dimensional systems, there are some papers which was started by Rodriguez and Hale. Rodriguez is former student by Jack Hale, and so I think it's correct to say that they started both to study synchronization in infinite dimensional situations, and then some others continue these studies. Then was some consideration of synchronization phenomena in non-autonomous case, and more recently people consider synchronization in stochastic situation. Here is also given some publications. So what we can understand from mathematical point of view under the notion of synchronization? Assume that we have a system of two coupled differential equations. It does not matter finite dimensional or infinite dimensional but the structure like this, and this is really my main example, which I will discuss here. Here nonlinear functions, here some noisy terms, which will be specified later. A1, A2 is are generators of C not semigroup, and for that system under synchronization, at this level we can understand. To give a flower in this level, we can understand the following. Assume that phase spaces of both equations are the same. X1 is equal to X2. Then they will say that in the system possible synchronized regime if they exist. If they exist solution, this is couple of two vectors, such that U is equal V for all moments time. They will say that they observe asymptotic synchronization if they have this property, the difference of two solutions goes to 0 and then T goes to infinity. So asymptotically, sorry?
What's the relationship between the first and the second noise? Are they correlated? Are they
You can look, okay, yes, they are correlated with, you mean noises or equations? Huh?
Are they correlated or independent? What is the relationship between N1 and N2?
They can be correlated and independent, but this is some general case. At this level, it does not matter how they're related. There are some perturbation. It can be even some functions.
But when you define the synchronized system, U equals
No, this is not definition. This is how to say, to give you a flower of what is synchronization. It's really notion is problem dependent, and each problem require their own definition. And it, yes. Oppa. So there are, roughly speaking, three possibilities to define synchronization. Possibility of synchronized regimes like this, asymptotic synchronization, U minus T goes to 0, or they can say about this even in a bit more general way, that some function of U and V goes to 0, then T goes to infinity. And I really will have these two examples of synchronizations. And one more synchronization, which is weaker than these two previous. This is the following. For example, you have global attractor from wall system. This is U, and this attractor is became product. In this case, here is a mistake. Here should be the same U1 U1. This is misprint. U1 times U1. So your global attractor is direct product of global attractor for one component on the same set for second component. So in some sense, the attractors, in some sense, these equations can be these sets can be interpreted attractor for each equation, but it's not correctly really. But yeah.
Do we assume that every solution behaves like this, or there exists at least one?
Possibility exists like one, and this is really definition for individual solutions. So two solutions, one solution became synchronized, and they can't. Then they say about synchronization, about this structure. They say really on global synchronization. Because all solutions goes to global attractor, and on the global attractor they goes to this set there 1 is equal to. So first example that they consider synchronization phenomena. Assume that they have some domain, gamma in AD, and some cylinders near this domain. So picture looks like this. You have gamma in AD, and here you have cylindrical domains. One of them denoted D1 epsilon, and the second one D2 epsilon. So they have this thin domain, and here in each domains D1 and D2 they have parabolic SPDE with white noise process, which is Gaussian, and it's important that it's not. It can be relaxed, but assume that this process depends only on the variable x prime. X prime is variable which is on the gamma, and other two variable x d plus 1, this is variable in this d. They assume that this, as you see, this is independent equations, and they assume that both functions satisfy Neumann boundary condition on external part of the boundary. D epsilon is a union of these domains, and some interaction, some matching condition on interface gamma. So that means that equations interact only via interface. Conditions which they assume more or less standard. This is some dissipativity conditions and prescribe the growth of functions f. Interface concerning interface reaction intensity, they assume that this is k is positive and converges to plus infinity after dividing over epsilon. This is really means convergence in Lebesgue measure. This means this one, that measure of points such that the less than goes to 0 for any n. And example of this k is simplest example, like this k naught is positive on the interface, and here epsilon alpha, then alpha less than 1. So they have these equations. K, I recall k is here. This is intensity of flow from one part to another concerning white noise. They assume these conditions. This is really rather restrictive conditions because it assumes some smoothness of covariance operator for this noise, and here beta is large enough, more than dimension over 4. And what else about system? This really model of reaction diffusion of two components filling thin contacting layer with this separating membrane, and the interaction between these two layers is possible only on the interface, and they have some noise on the interface, and our conditions concerning intensity K, it depends on the thickness epsilon, but it means our asymptotic formula means that this is a strong enough interaction between layers, and the really problem is to study this behavior is this model in two limits. Then epsilon goes to 0, small epsilon, and t goes to infinity. So I will deal with synchronization on the level of attractors. In order to explain this with more details, I first this is here perhaps I need to show this. So I said that they consider double limit, and it happens that in our case limiting system arises on the spatial domain gamma, has the following form. This is parabolic equation by this is one equation. It happens that this nonlinearity is mean value, and this viscosity and deterministic force are averaged the corresponding values of nonlinearity. This really would be limiting system which will describe asymptotic behavior of initial model. So in the descriptive way, result which I will present, this is a statement about synchronization at the level of global pullback attractors, and one more important observation, that if noise, which is common noise for all models, is non-generated, then they obtain stronger synchronizing effect than in deterministic counterpart of this system. This is really noise synchronized system. There is situation, then they are noise synchronized system. Perhaps this is the most interesting here. So first of all, I recall notion of random dynamical system, which is really can be written from book by Ludwig Arnold, and he was, I think, one of its founders of theory of random dynamical system. So assume that they have probability space, assume that they have some separable complete metric space X, and random dynamical system is a couple consisting of two objects. This is metric dynamical system on the probability space, This is consisting of family of measure preserving transformation which satisfy group properties, some measurability condition, and co-cycle. For this, the main property, this is this evolution, the so-called co-cycle property, and equations. One of the sources of random dynamical system. This is differential equation with stochastically or random perturbated differential equations. The need notion of random set, I recall it. This is set is random if this distance between any point to this set is measurable. They can introduce random closed set or compact set, and for theory of attractors for random dynamical system, important notion is all of temperedness. The set, the random set D omega is tempered if it can be included in some ball with this condition, which is depending on t. For all omega, it's grow less slower than any exponents. D calligraphical is collection of all tempered space. Now pullback attractor. This is a random closed set which is tempered. Is global attractor if they have invariance property for this set. For this co-cycle applied to U omega gives you a shifted set, and pullback attracting in this sense. Hausdorff semi-distance goes to zero for every omega, and this notion was introduced, I think, introduced and first studied by these authors. I wrote them in chronological way. Bjorn Schmalfuss, Hans Kraul, Franco von Dole, and other people continue this. There is some discussion why pullback, but I think everybody already participated in this. I only say that it's a pullback in this sense, but it's forward attractor, the dynamics in forward direction in this sense, in probability sense. And if attractor, some remark, consists of one point for each omega, then this point is stationary process. So this is some generalization of some notion which need you to generalize convergence to stationary regimes and systems. Main theorem which involve in model which I consider is the following one. There are several authors prove theorems like this, because this is really mimic of the corresponding deterministic result, but I took it from paper this author. For example, you can see this here. So if a system is compact for some time and you have some absorbing ball, tempered, then your attractor can be constructed like omega limit set. Now main results. First result, that coupling system for any epsilon generate a random dynamical system on this space, which can be considered like L2 space on the wall domain, and with co-cycle which is generated by solutions, and the metric dynamical system is generated by Wiener process in standard way. Limiting system, the system with averaged all data, is also generate random dynamical system in space L2. This co-cycle for finite time intervals are closed in the following way. You should integrate over d epsilon, this is union, and divided by epsilon, this is natural, because your domain is shrinking, and to obtain distance you should somehow to normalize domain. Next result, both systems have random compact pullback attractors, and epsilon and a naught, and most important that if correlation operator is non-generate, then limiting attractor u naught is singleton, so consists of one tempered variable. And as for synchronization, the result is related to this relation that attractors a epsilon are upper semi-continuous in the following sense. So the attractor for each omega u epsilon becomes closer to the global attractors of the limiting system. Under this condition, under additional condition that you have all data in both equations are the same and the function f is globally Lipschitz, then the observed effect that for epsilon small enough, this global attractor does not depend on epsilon. So they obtain that both solutions goes to u naught set, and for fixed epsilon. Here some remark. So if about singleton case, if u is one random variable, u naught limiting attractor, then they can rewrite upper semi-continuity relation in this form, and this implies that any solution becomes close to this one, so that they can find for any initial data that they have asymptotic synchronization in T and in epsilon. And under that condition, on the previous slide, they even have, they can remove this limit in epsilon, and thus they obtain synchronization in for finite epsilon. I would like to emphasize that in the case then correlation operator is 0, so there is no noise in the system. Under the same condition, they have no synchronization effect like this, and only on the level of attractors. So putting non-generate noise in the system give additional synchronized effect, and proof of this fact related to result which we obtained jointly with Mikhail Shoitsev from Berlin, and this really result related to describing of structure pullback attractor for monotone ADS. Here, if the assume that intensity interaction is not very strong, for example, in that sense, they obtain in this case they obtain two limiting equations, and to say about synchronization they can only in very special case. So this is mainly first part of my talk about synchronization via interface. It's was arises in some application, and it was main results was published in couple years ago in joint paper with Peter Kloiden and Thomas Karabalia. Now I will speak about the so-called master-slave synchronization. Master-slave synchronization. So I return to main object. We have two equations, two nonlinear equations, and two different Hilbert spaces. A are generator of strongly continuous semigroups, and F1 and F2 are nonlinear mappings, and the noise B N1 and 2 and some operator, this is white noise process, independent white noise process, independent, okay, we consider independent, and I will speak about it a bit later. So the goal is apply theory of random invariant manifolds in the study of synchronization phenomena in this system. Now about synchronization, I really explain what is mean, but now they can look on the synchronization like on the fact of existence and stability invariant manifold in the phase space of the system. For example, if they consider this manifold in product of two space, their U is E, are the same. For example, in the case x1, x2. So if this surface is invariant, this means that they can observe synchronized regime. If this surface is, for example, exponentially stable, they obtain asymptotic synchronization. And they really can look on this in more general thing, consider invariant surface of the following form, then one of component is function of the first one. And in this case, if there exist such invariant manifold of this structure, I assume that phi is Lipschitz mapping for each omega, then they can say about possibility synchronization, and if this is stable, they can say about asymptotic synchronization. Because globally stable property for this means that they have this asymptotic relation. Invariance means that U of t is phi t of v, and here the exponential stability means this relation. So one of the components became a function of another component, and therefore in this case speak about master-slave synchronization. The system for V is a master system, and U is the so-called slave system. And our goal to apply theory of invariant and inertial manifolds. This theory was developed by many authors. In deterministic case, we can show several monographs and a lot of papers about this. In stochastic case, concerning inertial manifolds, inertial, so invariant and exponentially stable manifolds, there is some publications starting from 1995 and so on. And there is several approaches to construction these invariant manifolds, and what they use in further consideration. This is presented a really deterministic idea due to Miklavchich of 1991. Okay, synchronization and master-slave means, by the way, that they can change, they can cancel one of the equation, put instead of u, instead of slave variable, function of v. So there is also, in addition, some reduction principle. What I will say now, this plan for this really second part. First I present main hypothesis, then discuss noise process which involve, then about existence of solution, then reduction principle and existence and stability inertial manifolds, then if I will have time I discuss distance between deterministic relation to random manifold to deterministic counterpart, and then discuss examples. So assumptions, the main assumption that linear part of the model A1 and A2 are generator, first one of C0 semigroup, which is exponentially stable. And as for A2, they assume that this is generator of group. So this can be continued in both directions, t to minus infinity and t plus infinity, with some prescribed growth on the negative semi-axis. These parameters m1, gamma 1, m2, gamma 2 are important in the estimates which will be described later. As for F1 and nonlinear mappings, they assume that they are globally Lipschitz with constant L1, L2. They are also go in picture. In space X, they introduce this norm. And I would like to mention too, in the so-called, in the case then gamma 1 decay of this C1 semigroup greater than gamma 2, their growth on the negative semi-axis this group. This comprises the so-called dichotomy estimates for this diagonal semigroup in the space X with respect natural projectors. Q is projected on the first component, pi on the second component. So they rewrite system as a first order equation. This is a standard. And now about noise. They really consider mild formulations, and they really don't need property of the they need really some integral property of this process. They consider this process n1 and 2 and assume that they can construct in some way Einstein type Uhlenbeck process eta 1, eta 2. Then it's possible to construct this process. I will give examples later, but our conditions, this is mainly about this eta 1, eta 2. First one, this is standard measurability conditions, R1, and they assume really to cover case of Levy process, they assume that they are Cadillac on S infinity for every S and minus infinity t for every t. And here measurability again, and here some evolution property. If you look on the integrals, you can make this kind of change of variables, at least formally. Here is also some evolution relation for eta 1 and similar for eta 2. And the most important that they have some stationary process for first component such that this limit exists for all omega, and moreover they assume that this is temperate random variable at n1. Now some integral conditions with respect to this noise. They need this function sigma. This is two components in space X, and they assume this integrability condition, which can be reformulated in the property of this process eta 1 and eta 2. This is really limiting stationary properties. This generates on this all process because stability of semigroup, but they no need this stationary process for the second component. Here is example, then all these hypotheses satisfied. It's for Brownian motion, it was checked in joint paper with Michel Shoitsev. For fractional Brownian motion can be found in a paper by Maslovsky, Smarfus-Maslovsky, and for finite dimensional stable Levy process, we refer to this publication. Then they introduce to cover all cases the space of Cadillac functions, and equip this not with standard for metrics for Cadillac functions, but with uniform with norm of uniform convergence. And in this case, we can consider in this space mild formulation of the problem, and easily to obtain existence of mild solution, and show that these solutions generate a random dynamical system by cocycle given this formula. And this cocycle continues for two of cases, and in the Cadillac version it's the results really the same. So only they have a Cadillac property in T variable. And the first result is existence. So if the parameters gamma 1 and gamma 2, gamma, this is growth parameters in linear path, m2, m1, this is estimates from linear path, and l2, l1 are estimates of nonlinearity. Then there exists random global Lipschitz function from x2 from x1. This is such that this set m omega is invariant with respect to the cocycle, so this relation is hold, and the attracting properties looks up. The manifold that in the cell that here attracting properties. This one, the constant. So integrals goes finite by this random variable, and here is growth exponent. So in some sense, this goes to 0 because integral exists. But if they assume a bit stronger properties of noises, then they obtain more or less standard exponential behavior. Proof, this is a more or less standard argument, fixed point argument in the corresponding space, L2 space, on the negative semi-axis with norm, which is defined with this term. And for this mapping, this is a really Perron method. I would like also to mention that invariance property implies that the have attracting in the forward direction is also so if R2 is temperate in the previous slide, some estimates, and this is at least true for the case of fractional Brownian motion and Brownian motion. Then they have property in both directions. So they have invariant attracting manifolds, and so they have master-slave synchronization. They can compare these manifolds with manifolds which correspond deterministic counterpart. So the system without noise. In this case, under the same conditions, they exist deterministic invariant manifolds, and they can estimate distance between this function, which is really distance between manifolds, in terms of process eta 1 and combination of process eta 1 and eta 2, which was described earlier. For example, in the case then we deal with Wiener process, they obtain this kind of estimate. So particular case for Brownian motion, if correlators goes to 0, then stochastic manifold became close to deterministic, so they have in some sense persistent of synchronization of deterministic system by stochastic perturbations. Now applications. There are several applications. They are listed here. I describe it. First one, this is couplet parabolic hyperbolic system. Assume that they have two elliptic matrices in RD, and let D is bounded domain with C1 boundary, and they consider this system. One equation is parabolic, the second one is a wave type equation. This kind of model arises Then you study wave phenomena in heat dependent or heat generating cases. They need to assume here that non-linearities, which is in here and here, are global ellipses with some constant global ellipses in R3 because we have free variable here. Then one can see that parabolic equations generate exponentially stable semigroup with estimated which is infimum of spectra of this operator A, one with Dirichlet boundary condition, and the second equations they write as a first order equation with B is that operator, and it's really a pure unitary semigroup as two linear part. If they equip the phase space x2 for a wave equation with corresponding energy norm, then they obtain these two nonlinearities abstract, and they can check that assumptions of imposed on the abstract system are true, and really calculate all variables which is present in the statement of on the existence of invariant manifolds, and so they arrive to the condition between low bound of spectrum and Lipschitz constant of functions, which shows that there is synchronized master-slave synchronization in this system. I would like to emphasize that it is not really important that D is bounded domain, only these properties we need for synchronization. The next example, this is couplet PDE and ODE. This motivated by the so-called Hodgkin-Huxley system in biology, and here they consider the same parabolic. For example, they consider this semilinear parabolic equation. Here is Laplacian with Dirichlet boundary condition, coupled with stochastic ODE, which in his turn depends on this solution, and this equations contains x and function u like parameter, so they need to solve this equation for any u of x. Here is described phase space. Operator A1 is minus Laplacian in x1, but A2 is operator, it's convenient to choose as 0. Then C2 is identity semigroup, and under this condition we have master-slave synchronization. Next example is two coupled hyperbolic equations. One equation with they need some dissipator to achieve exponential stability. They need that one equation should be with some dissipation, but the second may contain this kind of term, but may not. And in this case, they again have synchronization phenomena, but here they need some special. For the first component, they choose an energy norm, but for the second component, energy norm, but for the first component, some kind of norm, in order to achieve the better estimate for this gamma. If they choose gamma in this way, the first group would be exponentially stable, and calculations give again that the observed master-slave synchronization under these conditions on the operators and Lipschitz constant. So roughly speaking, we need to assume that Lipschitz constant for nonlinearity should be small enough. And last example, this is couplet Klein-Gordon-Schrödinger equations, which consist of wave equation and complex Schrödinger equation. And in this case, we also can apply this theory, but now one of the space would be complex. And here is really condition for synchronization. Here, for some diversity, I consider describe the cases then we have equation in AD, but if they consider bounded domain, they need to add some boundary conditions, surely. And so they also can see that this equation, Schrödinger equation, synchronize this one. So if they apply a reduction principle, they can exclude these first equations and simply put instead u some function of this v. So they arrive to modified Schrödinger equation. And I want to mention in conclusion that this first, that we cannot consider two coupled parabolic equations in this case, because we need special structure of spectrum of linear path. And the second one, that this results in the second part. This is mainly from the joint paper with Bjorn Schmalfuss, which is now submitted. Thank you very much for your attention.
Questions and comments? I would like to come back because somehow I missed. You said you have this attractor synchronization where the attractor is a Cartesian product. And do you have examples? I just kind of missed this part when you get this.
Well, this example.
You have a so it's not what can you again show it?
Yeah, just one. So we have this function. You can consider couple of function is like one function in the union of domain, and here for this function is written this relation. That means if you consider like vector function in one domain and two domain, they goes to one attractor. This is a naught attractor of limiting system, and this is exactly this diagonal structure. This is product structure u a naught times a naught.
Are there some more questions? I have one more question. It's really about your reference, but not your talk. You said that you have for monotone systems description of attractors in some work with Chueshov.
Yes.
So if you take a 2D Navier-Stokes equation, which is somehow locally, does not apply. Okay.
No. The main condition is monotone system.
But the 2D Navier-Stokes with kind of
it's not monotone in sense that you preserve order. Your space should some order relation, like positive function, and if we have relation between functions, the flow should transform preserve this relation.
So
this is not the case of Navier-Stokes equation. It's not applied.
I was saying that monotone in the system of Barbour whether this locally mounted in the sense
no.
of Barbu, whether this could...
No,
Okay,
not
we can do that later.
monotone in sense of positivity, standard positivity, monotone system. Not in the sense monotone operators of Barbu.
Okay, understand. Thank you. More questions? No, thank you very much.